When you run an update command in Postgres, it looks like you're simply overwriting an old piece of information with something new. But under the hood, Postgres doesn't actually touch the original data. Think of your database rows like blocks on an assembly line. When a change comes in, the system doesn't modify the existing block. It stamps out a brand new one and nudges the old version aside. That original row stays exactly where it was on your disk, becoming a ghost that Postgres keeps track of. Every row on a disk has a hidden header with two numeric stamps, xmin and xmax. Xmin records the transaction ID that created the row, and xmax records the one that deleted it. If xmax is 0, it tells the database that this specific version of the row is still live. During an update, Postgres writes a new row with a fresh xmin stamp. At the same time, it updates the old row's xmax stamp to match the current transaction. This allows both versions to exist simultaneously. By keeping these multiple versions of the same row, Postgres creates a way for different users to see different versions of the truth simultaneously. This is the physical foundation that allows for high-speed concurrency, where reading data doesn't have to wait for a write to finish. Having multiple versions of the same row scattered across the disk creates a routing challenge. When you ask for data, the database needs a reliable rule engine to decide exactly which version of a row you are allowed to see. Every time a query starts, Postgres issues it a snapshot. Think of this as a frozen picture of the database at that exact millisecond. It lists which transactions were already finished and which were still running when your specific query began. Your query compares the hidden stamps on a row against its snapshot. If a row was deleted by a transaction that started after your snapshot was taken, you ignore that deletion. You still see the dead row because in your snapshot's version of the past, that row is still the most recent committed data. Postgres double-checks a central commit log called pgexact to verify the status of those stamps. This ensures that the transactions listed as creating or deleting a row actually finished successfully and weren't aborted. This entire system, comparing row headers against transaction snapshots, is called multi-version concurrency control. It's the specific mechanism that ensures your read queries never have to block someone else's write queries. There is a physical trade-off to this design. Because Postgres never overwrites data, every single update and delete leaves a dead row behind that continues to take up storage space. On high-traffic databases, these dead rows can pile up into what we call table bloat. As the pile grows, the database has to physically scan past thousands of invisible rows just to find one piece of live data, causing your performance to drop. This is why Postgres runs a background process called vacuum. Vacuum sweeps through the physical pages on your disk and identifies rows that are so old no active query could possibly see them anymore. It marks that space as reusable, so new data can eventually be written over the old ghosts. In some cases, Postgres can optimize this. If you only update a column that isn't indexed, the system can chain the new version of the row right next to the old one inside the same physical block of storage on the disk. This bypasses a lot of the heavy lifting and keeps the database running fast. Tuning your automatic vacuum settings is essential. Without it, a busy database will eventually choke on its own invisible history, leading to massive storage waste and slow queries. Beyond storage space, there is a hard mathematical limit to the numbering system itself. Those xmin and xmax stamps use 32-bit numbers, which means Postgres can only count up to 2 billion transactions before the counter hits a wall. If the counter hits 2 billion, it has to loop back to 0. This creates a massive problem. Old committed rows might suddenly look like they were written in the future relative to the new low transaction numbers. Because they appear to have not happened yet, they become completely invisible to the database. Vacuum prevents this by freezing older rows. It replaces their numbered stamps with a permanent system ID, telling Postgres that these rows are from the distant past and should be permanently visible regardless of where the transaction counter is. If your write volume is so high that Vacuum can't keep up with the freezing process, Postgres will trigger an emergency safety shutdown. It will refuse to accept any new writes and enter a read-only mode to prevent catastrophic data loss. This isn't just a theory. Companies like Sentry and GitLab have faced total production outages because their databases hit this exact 2 billion transaction cliff before their maintenance tasks could finish. Monitoring the age of your transactions is the only way to ensure your database stays online. If you don't clear out those old IDs, the entire system eventually stops. Understanding these internal snapshots changes how we write code. As a developer, you have to choose an isolation level, which tells Postgres exactly how strictly it should handle these snapshots when your code is running. By default, Postgres takes a fresh snapshot for every single statement you run. This means the data could actually change between the first and second lines of your code, which can lead to subtle bugs in your application logic. You might try to fix this by using a stricter isolation level that keeps a single snapshot for your entire transaction. However, even a single snapshot doesn't protect against write skew. Here, two transactions both read a $100 balance. Seeing $100, both pass their check and withdraw the full amount. Both succeed using their own snapshots, resulting in an impossible negative balance. To prevent this in financial or inventory systems, you have to use explicit row locks or the serializable isolation level. This forces the database to guarantee that the final result is mathematically correct, even if it has to slow down to do it. When you use that strict serializable mode, Postgres will detect when two transactions are about to cause a conflict. Instead of allowing a logical error, it will intentionally fail one of the transactions and throw a serialization error with the code 40001. Your application code must be specifically built to catch this error. Rather than showing a failure to the user, your code should automatically restart the transaction from the very beginning with a fresh snapshot. Finally, from an operations perspective, there's one query every engineer should know: monitoring the age of your database's frozen transaction ID. You want to trigger alerts long before this number reaches the 1.5 billion mark. Mastering Postgres means balancing the massive concurrency of lock-free reads against the constant operational work of cleaning up the database's invisible history. Understanding MVCC is what turns a standard developer into a database expert.